Welcome back, Physics 30. Today's lesson basically conclude Unit C, Part 2 booklet. And this is a field where I can already see that people will have a hard time. I mean, look at the title. We're talking about the quantum mechanics. And lots of people hear about this quantum term a little bit more. And basically, you hear most of the time in the movies such as sorry, Ant-Man and Wasp or any type of Avengers movie, we're talking about quantum realm and so on. Long story short, if you perfectly understand the quantum mechanics, there's a little joke in physics. That means you don't understand quantum at all. Quantum mechanics is very theoretical and very philosophical field of science because we are trying to understand what makes us. And it's a concept of time involved too. So what we're going to go through is, like what I always do, I will try to not go over the curricular goal that Physics 30 have. And at the same time, we're going to cover as much as what we can from our algebra understanding. And have that in your mind that quantum mechanics or any type of quantum physics is still a developing field. So, history time again. The person who inspired the beginning of quantum mechanics at one point is de Broglie. It's a French graduate students who proposed some idea, and then it was actually seen by Einstein, if I recall, and this matter waves were accepted as it's possible. It was hypothesis at the beginning, but possibly it is theory accepted by the physicist. So let's rewind the clock a little bit. Compton's X-ray experiment perfectly proved that light is composed of particles. It's actually not wave because waves should be deflected and so on, and without the transferring the momentum like what particle does. Compton showed, and it was very conclusive evidence that high frequency EMR can have momentum, and therefore it behaves like particle. However, de Broglie suggested, due to a belief in symmetry, that matter could show wave-like property. So this is also going back to our Young's double slit at one point. Matter as wave. And when we talk about matter, generally we are talking about subatomic particle level. To make you understand that, you need to think about Bohr's theory, Bohr's atomic level at one point. De Broglie matter wave explanation actually supports Bohr's energy level state in each atom. In order to explain that phenomena, if you don't mind, I'm going to use a blank piece of paper. You do not need to prepare blank pieces of paper, but it's your choice. So, let's draw hydrogen. Hydrogen is easy because you have one proton and one electron. Oops, actually shouldn't have a neutron, sorry. So nucleus at the center, an electron orbiting at ground level. Now let's think about everything in terms of matter as particle situation, so as photon. If you think about that perspective, we know that there is an error. electron is or are, depends of how many, orbit around the nucleus, proton in this case. Now the problem is, because it have centripetal acceleration, that means you have net force, Fc, centripetal force, and because you have force and acceleration, you should emit EMR, and that's done by Maxwell. And at the same time, because you emit EMR, as time go, whatever time passed, you should expect a little collision between electron and proton in this case, because your circle will go smaller, 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 and collide. That's what should happen, because you're gonna lose basically kinetic energy because it transfer into EMR energy, omit of the photon. But this was one of the main problem in Rutherford and main problem still in Bohr situation. Now, de Broglie situation. His idea was this: if electron are located at its ground level or whatever the level, atomic level, that electron belong, then at that part, this matter behave like wave. And in fact, wave property works for that scenario, because let me draw a wave. Imagine this electron is a starting point, up, down, return, up, down, return, up, down, return, up, down, return. Although it is an ugly picture, but you may notice that there is a wave that going propagated direction, which is circular, but you may notice up, down, return. That's one wavelength. Up, down, return, another wavelength. Up, down, return, another wavelength. Up, down, return, another wavelength. So you may notice that because it's wave, they do not lose energy. In fact, wave send and transmit energy around it. And another benefit of that is it's quite stable as long as you stay in there. Then how come this matter behave like particle, like in Compton? What de Broglie suggested was, if this electron move around, if you go up or down to another level, atomic level, that's the only case where you see particle type of behavior. So his theory is one of the ultimate model that suggests the idea of wave-particle duality. Because if we assume that at energy level it behaves like wave, this theory works. Bohr's theory makes sense. Bohr's theory, in fact, perfectly can be explained, and so as combined with Rutherford, the orbital model work. However, the only time it changes like particle and go is when these waves are now packed and go from one level to another. That's where you will start to see particle-like behavior. So particle and wave, discussing these two is in fact silly, because matter have both properties. So here's what I want to point it out here. His suggested that due to a belief in symmetry that matter could show wave-like property, he introduced the idea of wave-particle duality in particles. Not only EMR, every matter, electron, proton, neutron, the subatomic particle. And the formula come out like this. Again, we are not deriving the formula. Lambda wavelength is equal to h over p. As you may notice, p is momentum. So by having p inside of his formula, it mathematically involve not only particle, but also if you look at lambda, that's wavelength. So you may notice that particle-like, wave-like formula all the way together. And from Compton's P is equal, from unit A, we learned that P is equal to mv. If we involve that together as one formula, we're gonna substitute mass and velocity or speed instead of momentum. We know that h is Planck constant, lambda is wavelength in meter, m is particle's mass, and v is speed of the particle. So let's do one example. A particle moving at a speed of 6.50 10 to the power 7 meter per second has a kinetic energy of 25.0 kilo electrovolt. Determine its wavelength. So we have a question over here. We know that speed is given 6.50 10 to the power 7 meter per second. Kinetic energy EK also given 25,000 electrovolt. I like to get rid of those kilo or those kind of prefix for SI system, and determine the wavelength meter. Here's what we can do. Wavelength is equal to h over p, which is equal to h over mv. Now it says a particle that has a kinetic energy of that. As you may notice, mass we don't know. So we don't know the mass in addition to what's going on. But using the kinetic energy, we can find mass because, and now we're going to do a step-by-step situation, because EK is equal to 1 over 2 mv squared. As you may notice, m is involved. We just need to isolate for m in this situation. So if I isolate it, m is equal to 2ek over v squared. 2 times kinetic energy divided by v squared. In order to do that, of course, you may notice we need to convert electrovolt into joule by multiplying the conversion. Don't forget to squaring the v. And now we are punching the number in. Then 1.89 10 to the power 30 kilogram is what is given as a mass. Even though I put a rounded answer, I want you to keep the actual number in your calculator. It goes like 1.89349, those kind of numbers. Number 2, now we can substitute everything in inside of the de Broglie formula. Planck constant first, followed by mass, followed by the speed. Then you have 5.39 10 to the power negative 12 meter, or 5.39 picometer, something like that. So it is an X-ray. Note the fact that when it comes to de Broglie formula, it works when the speed is definitely less than speed of light. In fact, we haven't discovered any of a particle that is faster than speed of light, so I have that in your mind too. The one that support this evidence of matter wave is basically two-slit experiment like Young's double slit. Very similar, except instead of light, we shone upon electron. If we are thinking about any type of particle as a matter, so what I'm talking is any subatomic particle behave like particle, then if we shoot this beam of electron, you should see a beam of light only through that opening. So you should have one bright light, two bright light. But the funny thing is, scientists observed band of light, node and antinode, and nodes, or maxima and minima, just like Young's double slit. Which is very similar result as what Young's double slit experiment was done. And because of this, we found that electrons, despite the fact that most of the time it behaved like particle, it showed evidence of diffraction and interference like wave. So now this is a part where quantum mechanics started. What is matter smaller than subatomic particle? So even though, for example, my finger and my skin cell, my bone cell, muscle cell, those are actual physical particle. However, when you go even deeper level, it seems like it composes a wave. So we are wave that have a form. How that's possible? So this indication basically show that electron have wave properties, and this is one of the key finding that wave particle duality of particles is now carved stone in modern physics. Quantum mechanic model. This is a trigger part. Some people know Schrödinger and then cat in a box situation, and I try to go as easy as I can. Electrons are kind of like a cloud, to be honest. In reality, it's not countable matter. It used to be believed in that way, but not in 21st century. But scientists basically now start to have a question. What is an atom? How can this wave slash particle matter exist inside of an electron, proton, those situations? There are growing evidence there where electron is orbiting around the atom, but they behave more like wave, and that's what I show you as a drawing. The one that act as a wave at a level that electron belong. This basically proved that wave have no definite position. And that makes sense. Like, for example, imagine you are trapped inside of a space where it's repeating and repeating, and there is a wave that is coming out. And where do you know where the wave is originally staying, or position of the wave? If you locate that position of the wave, it's funny thing is that wave, it's going to move away from you. So from my picture, for example, imagine this is where you want to see the wave and identify. You've calculated the location, but if you actually went there, this wave is now somewhere over there. Because wave is constantly moving. The source of the wave and location of the wave, everything was so complex. Because wave have no definite position, but at the same time, it's spread over to way much larger area. So one scientist, Heisenberg, basically claimed that it was impossible to know the exact location and momentum of that wave at the same time. This is Heisenberg uncertainty principle, because everything is moving and spreading a lot in the world of wave. So rather than placing an electron in, this electron stay over there, like Rutherford and Bohr suspected, and you guys learn in that way, 2, 4, 4, 8, those kind of thing, the first level, ground level, second level, third level, all the way to valence electron. Scientists were forced to consider the location of an electron as a probability function now. And that model shown down there. Quantum mechanic model of hydrogen as an example, which has only one ground level, right? You will see a lot higher density at this location. And that's our ground level n equal to 1, which is that shaded one over here. And the thing is, that's where we know that it has high possibility of detecting electron. It's quite dense. It's a cloud of electron, to be honest. However, if you go outside, you start to see low probability of locating electrons. So we are talking about more density situation. The high probability area is known as an orbital, and this is where we would most likely find the electron. But when it comes to low probability, it could be somewhere other than this level. So these probability, one thing you need to understand is it can be calculated precisely. Just like exact prediction at dice or playing card, like for example, what's the probability of having red color in this deck of cards? Well, you know that it's 50%, 50, because it's half of them are red, half of them are black, something like that. Or I throw the dice, what's my probability of having 1? That's 1 out of 6. But these are not like probability that you see in that kind of, what is it called? Like limited outcome and then finding out the probability. It is different. It is more, it is, how can I say in an easy way? It's not like chaos theory where you need to think about one outcome affect the another outcome. We're not talking that because nature have its own law. And we're trying to find that law, and mathematically it was possible. There's some assumption, but still. This quantum mechanic model of the atom has been incredibly successful in predicting atomic behavior, and its basic structure has not changed since 1930. We still use it for over 70 years, and this is an amazing consideration of all technological advances since then, because we now understand this mechanism, at least where it's located and so on. It's like we have a hunch. It's like, imagine you're going hunting. You see a footprint. You know that that's moose footprint or wolf footprint, bear footprint, something like that. We may not necessarily find the bear. I hope that makes sense with you as a little bit of a analogy. It remains our best mathematical description of the atoms to this date now. So how can we evaluate quantum mechanic model? Well, the quantum mechanic model could answer most of the question that Bohr had as a trouble. First thing first, the spectra for more complex atom with more than one electron, it behaved because there are more higher probability density. That's why it's more complex spectra. Why only certain orbits were allowed? Well, it's because they have stable standing wave at this orbit, so they don't emit EMR, which is what connect to the next one. Behave like waves, so no longer behave as accelerating charge. So that's why we do not emit EMR. And last part, why some spectral lines were brighter than others is because quantum theory, when you think about the energy level and instead of matter become a particle like electron, it behaves as waves. So certain transition have a higher probability of having that emission happen, or having more, how can I say, it has more photons coming out from that area, which is the reason why we have brighter zone compared to the others. So long story short, ladies and gentlemen, the quantum mechanics is an interesting field, and then there are a lot to study when it comes to that field because we basically don't know a lot about that. we still haven't had a major discovery after that. Even the gravitational wave and so on, those are the ones that we now can detect using our technological development. We still don't have any theoretical creativity that many now they're all passed away. Many physicists we had in 1900s, which is what we see at the very front of this page. Even though you cannot see a lot, I put that as a little PDF file. We have quite a lot of physicists who play a huge role. Anyway, that is a little bit of respect that we should have. Your to-do list is page 72 and 73, and I want you to work on those questions as a homework.